Okay, so last time we were talking about, let's just do a recap. With so many disruptions. And recap of last time. We're talking about hydrohalogenation, in which an alkene reacts with HX. X is just the generic symbol for the halogen. It could be chlorine, bromine, iodine, or fluorine, or whatever. And what happens is the carbon-carbon double bond is degraded to a single bond, and the elements of HX add across where the double bond used to be. The mechanism of the reaction involves a carbocation. So the first step is the double bond attacks the H end of HX, and we get a carbocation. And we talked about how a carbocation is a high energy species. It only has a sextet of valence electrons. And we talked about some of the structural features of the carbocation, that it is sp2 hybridized, it's planar, it's electron deficient, and we talked about the stability of the carbocation, namely that resonance stabilized carbocations are better than tertiary, are better than secondary, better than primary, and better than methyl. So this is the most stable kind of carbocation, and this is the least stable kind. And we talked about the reasons for this is that the carbocation is electron deficient. Resonance can dump electrons into the carbocationic center, then that is going to stabilize it. A degree of substitution can also donate electron density to the carbocationic center, and that stabilizes it. Anything that can pump electrons into the carbocation is going to stabilize it, whereas anything that further diminishes the electron density at the carbocationic carbon destabilizes it. Okay, and so to finish up this mechanism, now the X minus, that's the nucleophile, the carbocation is the electrophile, and so the second step of this reaction, the Cl minus or Br minus or I minus or whatever this is in here, comes in and picks up that carbocation, and there's the mechanism for the reaction. Okay, so that's what we talked about, that's what we were talking about last time. All right, so now one of the things that I would like for you to focus on as you're studying this material is the skill of product prediction. And so many times we don't even need to know the mechanism of the reaction to be able to predict the products of what's going to happen. Let's look at this. Let's look at this problem here. So what would be the structure of the product? So draw the structure of the product. So there's my carbon-carbon double bond. It's going to be degraded to a single bond, and the elements of HCl are going to add across where that double bond used to be. But now we're at a crisis, because the first step of the reaction mechanism, the double bond attacks the H end of HCl. But now we see in this situation, we have two options. So we could have the double bond attacking the H end of HCl. But in this case, we're going to get two different options depending on where that carbocationic center is going to form. it could either form there, and the proton went on this carbon here on the right, or we could switch up. And see, the first step of this reaction mechanism is the double bond attacks the H of HX, and you get the H ends up at one end of where the double bond used to be, and the X minus is swimming around in solution. But when but in many cases, we have two ways of degrading that single bond to a double bond. We have two ways of where to put the H, and we have two ways of where to put the carbocation. Okay, so these are the two possibilities. Tell me in the chat, if anybody is still there, tell me in the chat which of these structures is going to happen. Is it going to be the guy on the left or on the guy on the right? It's going to be the one on the right. Why is that? Because this is the more stabilized carbocation. That's tertiary. This is secondary. That doesn't happen, but this does. Okay, and so now the last step of this reaction would be the capture of the carbocation by the chloride, capture of the carbocation by the chloride, and that would be our final product. So the Cl ends up over there, and the H ends up over here. Okay, this is an example of the famous Markovnikov's rule. And so this is named after a Russian scientist in the 1880s who first observed this behavior. This is called Markovnikov. So I've seen this name spelled 100 different ways. I'm writing it with B's, but I've seen it with W's, I've seen it with F's, I've seen it with double F's. Forget about that. Markovnikov regio selectivity. So when you hear me say when you hear me say Markovnikov regioselectivity, or if a reaction exhibits Markovnikov regioselectivity, what I am saying, and I'm just going to put it right here because I don't need any more room. What does Markovnikov regioselectivity mean? Means the most stable carbocation is formed is an intermediate. Right, so that's Markovnikov regioselectivity, and that's the Markovnikov rule. So just to recap, is that you're going to have a double bond. You could put the positive charge on one end or the positive charge at the other end. And so we need to be able to predict what is going to happen. Okay, so let's do some more problems where we're showing Markovnikov regioselectivity. All right, so what if I were to ask you to draw the structure of the product here? So a couple of different points. First up is that benzene ring is not an alkene. It's represented as an alkene for historical reasons. So none of these reactions I'm talking about are going to put involve any of the formal double bonds of benzene, right? So the double bond that's going to react is going to be this one over here, because that's not part of a benzene ring, and benzene is not an alkene. None of these reactions monkey around with any of the bonds of benzene. So tell me where that BR is going to go. Tell me here in the chat. Is the BR going to go at 12 o'clock, Or is the BR going to go at 2 o'clock? Okay, it's going to go at 12 o'clock because my two options are in for that first step, for that very first step, something like that. For that very first step, I could put the H at 12 o'clock, or I could put the H at 2 o'clock. And what do I see here? A resonance stabilized carbocation. So I can draw all kinds of resonance structures in which I'm moving these bonds of benzene to stabilize that carbocation. So, I'm just going to write one resonance form, but there are others. So I would get something like that. So that's a resonance stabilized carbocation. This doesn't happen. This is the choice that actually obtains. And so in the second step of the reaction is the capture of the carbocation by the nucleophile, which is Br minus. And so this is another example of Markovnikov regioselectivity. All right. So let's try one more. Okay, so that looks very friendly there. Hi, but it's actually hydrogen iodide. Draw the structure of the product. That double bond's going to go away, right? It's going to become a single bond, and you're going to get H at one end of where the double bond used to be, and I at the other end of where the double bond used to be. Tell me in the chat, where does the I end up, on the left or on the right? Where does the I go, on the left or on the right? Oh, sorry, this is supposed to have a 2 on it. Sorry about that, Me2. Okay, so tell me in the chat, where does the I end up, on the left or on the right? It's going to end up on the left, but not for a lot of the reasons that people are telling me in the chat. Okay, so first step, here are the options. Which one looks better? It's going to be this one. Why? Because this is resonance stabilized. It's not because it's primary or secondary or anything like that, because this is a resonance stabilized carbocation that is stabilized by the electron pair on the nitrogen. Right, so that's no good. This is just a primary carbocation, really bad. This is a lot better. And so in the second step, the I minus captures this carbocation, resonance stabilized. And so that would be the product. Yes? Okay. Now, this is usually the time that I like to take my break to drink some coffee, but no break today. Okay, so let's look at this situation now. So I'm interested in this reaction. Draw the structure of the product. And while you're thinking about what the product is going to be, let me show you the NMR of the product. Okay, so the product is a compound of formula C6H13Br, and the NMR spectrum, everything is between 1 and 3 ppm. So here I have a septet, and here I have a singlet, and over here I have a doublet. Okay, and this septet integrates for 1 hydrogen. The singlet integrates for 6 hydrogen, and the doublet integrates for 6 hydrogen as well. So what are we thinking about what the product, what the product should be? Well, here we have this double bond is going to get knocked out. We're going to get positive at one end of where this double bond used to be, H at one end of where the double bond used to be. But we just talked about how we have 2 different possibilities. So what I would like to write is that, right, I got a secondary carbocation. That's better than a primary carbocation. And that was the intermediate. Now that intermediate is intersected by Br minus, and so I'm looking for that as the structure of the product. But when I do this experiment and take the product into the NMR room and record its NMR, is the NMR of the product consistent with that structure? Tell me in the chat. 50-50 chance of being right just by guessing. Is that predicted product, is it consistent with the NMR? Oh, very good. Lots of people said no. Well, this guy is going to give a 9 hydrogen singlet. It's going to give a 1 hydrogen quartet, and it's going to give a 3 hydrogen doublet. I didn't see any of that here. What happened? Okay, so what happened is a complication that arises with this hydrohalogenation and many other reactions, and that is the carbocation rearrangement. So this is not, we don't get any of this. We get 0% of that, and instead what we get is something that looks like this. Okay, so now does that fit? I'm going to have a 1 hydrogen septet at that fishtail. Yep. I'm going to get a 6 hydrogen singlet due to these guys and their downfield compared to the other 6 hydrogen signal, because these guys are closer to the bromine, and then I'm going to get a 6 hydrogen doublet over there. Okay, well, what happened? It looks like the HBr clean missed where the double bond used to be. So what happened here is the carbocation rearrangement, and so that's what we need to talk about now. Carbocation rearrangement. So this is something that carbocations do with alarming frequency. If they are usually a nuisance in the laboratory, but if you're a great genius of organic chemistry, you can actually exploit the carbocation rearrangement to come up with something that you want. Okay, so let's talk about how a carbocation rearrangement works. Call the carbon. So before a carbocation can rearrange, we have to have a carbocation. So there's my carbocation. And the carbon that has the positive charge, I'm going to call him carbon 1. The neighboring carbon is carbon 2. And some molecules can have up to 3 carbon 2s. The carbocation is here, but you can have 3 carbons bonded to the carbocationic carbon. Here I'm just showing 1, but we need to remind ourselves that carbon 2 is just the neighboring carbon. There is something bonded to carbon 2. I'm going to call that Z. Z is usually, it doesn't have to be, but most of the time, Z is going to be a hydrogen or an alkyl group. So, in a carbocation rearrangement, something, Z, pulls out of carbon 2, migrates over to carbon 1, plugs into carbon 1, and the charge moves in the opposite direction from 1 to 2. Okay, so I'm going to picture all of that. Here is a C group pulling out of carbon 2 and plugging into carbon 1. This is the migrating group. So this is the transition state. I'm going to put it in brackets. I'm going to put a double dagger up there to show that's a transition state. And because I believe in charge conservation, this transition state has a positive charge somewhere. I don't want to get into where it is. Let's just say, let's just put the superscripted positive charge there, showing that there's a positive charge remaining. Okay, at the end of the rearrangement, the group has pulled out of carbon 2. It's pulled out of carbon 2. It's plugged into carbon 1. And the charge has moved from carbon 1, where it was initially, to carbon 2. So that's a carbocation rearrangement, a mechanism for the carbocation rearrangement. Now, these rearrangements, although they are a nuisance, do not happen willy-nilly. They're not random. Is that we can predict that a carbocation rearrangement will happen when we can go from a less stable carbocation to a more stable carbocation. That's where we can expect to see a carbocation rearrangement. So less stable carbocations rearrange to more stable carbocations. So that's one of the reasons why having a good handle on the order of carbocation stabilities is important, because now we can see we're better positioned to predict when a carbocation rearrangement is going to happen, and when we see a reaction in which we have rearranged products, we can understand it better if we know about the carbocation stability trends. Okay, so let's go back to our original problem where I presented that NMR, and let's try to understand what's happening there. All right, so I had this, and react to that with HBr. First step of the reaction mechanism is the protonation of the carbon-carbon double bond with Markovnikov regioselectivity. In other words, the most stable carbocation is formed. And so in this case, that's going to be secondary like that. And now it's time for the rearrangement. We call the carbon that has we call the carbocationic carbon, carbon 1. We call the neighboring carbon, carbon 2. This guy has 2 carbon 2s, one on the left and one on the right. Something bonded to carbon 2, and that something is always going to be either a hydrogen atom or an alkyl group. Something bonded to carbon 2 pulls out of carbon 2, plugs into carbon 1. The charge moves from carbon 1 to carbon 2, but the rearrangement happens only when we can go from a less stable carbocation to a more stable carbocation. So let's analyze this problem. So something bonded to carbon 2. Well, there's only a hydrogen atom bonded to carbon 2. He could pull out of carbon 2. He could plug into carbon 1. And the charge would move in the opposite direction from carbon 2 to carbon 1. So there, I pulled that hydrogen atom out of carbon 2, plugged him into carbon 1. I moved the charge from 1 to 2. And we see this would never happen because I'm going from a secondary ion to a primary ion. No good. Right, so I don't have to worry about the locus of the rearrangement being on the right-hand side of this molecule. All right, so let's try again. Something bonded to carbon 2, a methyl group, is going to pull out of carbon 2, and it's going to plug into carbon 1. And the charge is going to move from carbon 1 to carbon 2. Well, that makes a lot more sense. That makes a lot more sense because what I'm doing here is I'm going from a secondary ion to a tertiary ion. And so that is downhill in energy. That is a less stable ion rearranged to a more stable ion. And then the final step of this reaction mechanism is the capture of the carbocation by the nucleophile. And so this is the structure of the product that we drew a few minutes ago, for which I gave you the NMR. And so now we see how this reaction has sort of messed up and gone from we still got the elements of HBr were added to the molecule, but not in the simple way that we had been entertaining up to now. Okay, so that's a carbocation rearrangement. Let's do some practice problems writing mechanisms for carbocation rearrangements. Okay, so let's look at this guy. We add HCl. And what is the product? Oh my God. So that's the product. So you see a whole lot has happened here, right? That square is gone. It blew up into a pentagon. And this double bond here sticking out like an ear on the side of this molecule, where is he? Wow. So when the carbon skeleton has been reorganized like this, this is a clue to us that a carbocation rearrangement has happened. So let's go through the mechanism, the electron pushing mechanism for this rearrangement. And while I'm going through this, I also want you to pay very close attention to my use of the curved arrows. Remember, the curved arrows represent the motion of electrons and not the motion of nuclei. Okay. First step, ho-hum, everything just totally normal. That double bond is protonated by the HCl with Markovnikov regioselectivity. In other words, the most stable carbocation forms. So I could put the H on the left, or I could put it on the right. I'm going to put the H on the right. That way I get a secondary carbocation rather than a tertiary carbocation. And I'm not going to write that H anymore, right? Because it's there and we know about the bond line and all of that, but it's an H. Okay, and now all hell breaks loose because now it's time for the carbocation rearrangement. We need to figure out a way to blow this 4-membered ring up into a 5-membered ring, but remembering all the way that we're going from a less stable ion to a more stable ion. So there's carbon 1, there's carbon 2, there's carbon 2 over there as well. Something bonded to carbon 2 pulls out of carbon 2, plugs into carbon 1. The charge is going to move from carbon 1 to carbon 2, but it's going to create the most stable carbocation. So on carbon 2 on the right, we have hydrogen. Hydrogen could pull out of carbon 2. It could plug into carbon 1. The charge would have to move from carbon 1 to carbon 2, but that's not going to happen because that's going to convert a secondary to a primary. No good. Let's look at the other carbon 2. What all is bonded to carbon 2? I have a hydrogen bonded to carbon 2. He could migrate. I have this carbon down here. I'm going to put a dot on him. He's bonded to carbon 2. And I have a carbon over here, this carbon atom over here. I'm going to put a square on him. He's also bonded to carbon 2. So what I've done is I've identified the candidates for the migration. And in order to write the mechanism for this reaction, I'm going to see which one makes most sense. Okay, so what if this hydrogen moves over, right? What if this hydrogen pulls out of carbon 1, plugs into carbon 2, hydrogen pulls out of carbon 2, plugs into carbon 1, and the charge moves from carbon 1 to carbon 2. That would be the ion that I would get as a result of the rearrangement. But this doesn't happen because I need to blow that 4-membered ring up into a 5-membered ring. This is secondary, this is tertiary. Am I going from a more stable ion to a less stable ion? I'm not. What is so terribly wrong? Tell me in the chat, what is so terribly wrong with this tertiary carbocation? Why doesn't this happen? I have to blow that square up into a pentagon. This rearrangement doesn't blow the square up into a pentagon. It keeps the square a square, even though I'm going from secondary to tertiary. That's the thrust of my question. Why? What is so terribly wrong with this tertiary carbocation? Way too much strain. Yes, thank you, everybody. The carbocationic carbon is sp2 hybridized. That means its ideal bond angle is 120 degrees. Here, this is a horrendously strained tertiary. It's probably less stable than the secondary, right? So this doesn't happen. Okay, so I've identified the candidates for the migration and I'm discounting them one at a time. Okay, now what about the square? What if the square pulls out of carbon, the dot? What if the dot pulls out of carbon 2 and plugs into carbon 1? All right, so we're going to get something that looks like this. There's the dot. He used to be bonded to carbon 2, so I drew those dotted lines showing that the dot is pulling out of carbon 2. And now he's plugging into carbon 1. More dots, meaning that more dashes, meaning that the dot is moving over to carbon 1. That's the transition state for the rearrangement. At the end of the rearrangement, the dot has pulled out. The dot has pulled out of carbon 2. It's plugged into carbon 1, and the charge, right? This was my carbon 2. There's my carbon 1. This is my carbon 2. There's my carbon 1. Something has pulled out of carbon 2 and plugged into carbon 1, and the charge has moved from 1 to 2. That's what blows this square up into a pentagon. All right, so now I'm not going to go through the motion of this square. I'll leave that up to you. You get the same thing, right? You get a square blowing up into a pentagon. So this is a hideously ugly drawing. Let's fix it. Right, so that's just a 5-membered ring with a positive charge somewhere, and then on the next door carbon, there's a methyl. Okay, and so now what's supposed to happen is that the Cl minus, that's the nucleophile, is now supposed to capture the electrophile, which is this C plus. Is that what happened? Is the Cl minus going to attack here now? Oh no, because the product doesn't have, the product isn't 1-chloro-2-methyl. The product is 1-chloro-1-methyl. So not finished yet with this mechanism. What happens next? Tell me in the chat. Another carbocation rearrangement, definitely. This is carbon 1. This is carbon 2. Something bonded to carbon 2, in this case a hydrogen atom, is going to pull out of carbon 2. It's going to plug into carbon 1. And it's going to do that because a more stable carbocation can be produced. So there's the hydrogen pulling out of carbon 2, plugging into carbon 1. The charge has moved from carbon 1 to carbon 2, and now, finally and at last, the Cl comes in, captures the carbocation, and so there's my reaction mechanism. That's how this reaction works. Okay, couple of things to say about this mechanism. Notice in this rearrangement, I've gone from a secondary ion to another secondary ion. But wait a minute, I thought that these carbocations rearrangements only happen when I'm going from less stable to more stable, but that's what I'm doing here. This is a secondary ion with a lot of strain going to a secondary ion that has much less strain. So you're going downhill in energy. Not all secondary ions are created equal, obviously. Okay, now the second rearrangement, we're going from a secondary to a tertiary carbocation, right? And we're not introducing more strain or anything like that, so the second rearrangement makes a lot of sense. All right, another thing I would point out to you about these carbocation rearrangements is that they are lightning fast, right? Positive loves negative. There is an irresistible attraction of positive or negative. Yet, this carbocation does all of this rearrangement while the Cl minus is just sitting around in the solution looking for something positive to react with. The carbocation rearrangement is much faster than the rate of the carbocation rearrangement is much faster than the rate at which positive charge can find negative charge in solution, right? Because the the negative, the positive and the negative, they have to swim around in the solution. They have to find each other. That's called diffusion. The rate of a carbocation rearrangement is faster than the rate at which species can diffuse through the solution and find each other. So these carbocation rearrangements, lightning fast. This guy rearranged twice before the Cl even got in there. Okay. So let's do another carbocation rearrangement mechanism. But how about something now a lot more challenging? Also something that's a lot harder to draw. It's a 5-membered ring which is fused to a 7-membered ring. Those are always hard to draw. We have a methyl group there, a methyl group there, and a double bond there. React this with HBr, the product. Oh my God. Is that? Write a mechanism. Use the curved arrows to show the motion of electron pairs, right? I'm telling you what a problem like this is going to look like on the final. Write a mechanism and show the motion of electron pairs using those curved arrows. You know that a carbocation rearrangement was involved because the skeleton has reorganized itself. That 5-membered ring shut that, blew up to a 6-membered ring. That 7-membered ring shut down to a 6-membered ring. We have this reorganization of the skeleton. So that's our big clue of a carbocation rearrangement. So let's go through what the mechanism would be. First step is the protonation of the double bond with Markovnikov regioselectivity. In other words, I'm going to put the positive charge on the tertiary part. So it's hard to draw. It's a 5-membered ring fused to a 7-membered ring. Methyl group there, positive charge there. Right, so there's my tertiary carbocation. I chose that in preference to the secondary carbocation. All right, and so now it's time for the rearrangement. So this is carbon 1, this is carbon 2, this is carbon 2, this is carbon 2. I got a lot of possibilities, a lot of choice. I'm trying to identify the candidates for the rearrangement. I can dismiss 2 of them right out of hand. If I take this positive charge on carbon 1 and move him up here to carbon 2, I'm going from tertiary to primary, no good. So the rearrangement's not going to involve that carbon. If I take this positive charge from this tertiary carbon and move it from carbon 1 to carbon 2 to the secondary carbon, I'm going to go from tertiary to secondary, no good. Right, so all of the action is going to be on this carbon right here. And I have a lot of candidates for the migration. So this methyl group could migrate. But it's not going to, because then I'd be just going from a tertiary to another tertiary with the same amount of strain. Or there's carbon 2, this guy, the dot, he's bonded to carbon 2. He could pull out of carbon 2. He could plug into carbon 1. And I have this guy over here, which is the square. He's bonded to carbon 2. He could pull out of carbon 2 and plug into carbon 1. All right, so I've analyzed this, and so so I've looked at all of these possibilities, and by a trial and error procedure, There is no flow chart, right? There is no, well, if this, then that. Just by a trial and error procedure, I determined that the best carbocation rearrangement is going to happen when this dot pulls out of carbon 2 and plugs into carbon 1. That's going to blow this 5-membered ring up into a 6-membered ring, and that's going to shut this 7-membered ring down to a 6-membered ring. So it's this dot that migrates, and I'm using these curved arrows to show that migration. Dot, 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 dash, 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 dash. There's the dot, there's the bond between carbon 2 and the dot. That's going away. Carbon 2 is pulling out of the dot is pulling out of carbon 2. Dash, 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 dash. The dot is plugging into carbon 1. There was my carbon 2. There's my carbon 1. Carbon 1 was part of the 7-membered ring. Boom, boom, boom. So there's my transition state for the rearrangement. Maybe put him in brackets, double dagger to show he's a transition state. I'm showing the dot pulling out of carbon 2 and plugging into carbon 1. All right, at the end of the rearrangement, I'm getting something that looks like this. That bond is gone. Boom, 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 methyl group. And the charge has moved from carbon 1 to carbon 2. See, so now this is a hideously ugly drawing, but what I see here, 1, 2, 3, 4, 5, 6, and back again. That's a 6-membered ring. What I see over here is 1, 2, 3, 4, 5, 6, and back again. That's a 6-membered ring as well. So just to clean this up, I'm going to write it like that. And so this is the rearrangement that is going to give me those 2 6-membered rings. Now, finally and at last, the Br minus can come in here and capture this carbocation. And so there is my product. Okay, so what you're doing when you're dealing with these problems is that you are looking for the skeletal the reconfiguration of the skeleton. That is going to suggest a carbocation rearrangement where the carbon skeleton somehow got changed. And then you have to identify candidates for the rearrangement that are going to proceed toward the actual product that is observed. All right, so these carbocation rearrangements, I don't know if you're planning to be around for Orgo 2, but they're never going away if you're going to be around for Orgo 2. Okay, so that's it for hydrohalogenation. Let's look at our next reaction, which is halogenation. Okay, the overall reaction is we have an alkene, right? Because we're talking about the chemistry of the alkenes. We have the alkene, and we react it with X2, right? And so this, it could be F2, but it never is. So this is going to be either Cl2, Br2, or I2. And this is something that should be there, should ring a bell with you, right? Because we just talked about radical reactions, and we saw that Br2 and Cl2 were very prominent there. what is the difference between what we're talking about now and what we talked about with radicals is that this reaction is going to happen at 25 degrees, right? Don't have to heat it. Remember when we were talking about radical reactions, we always had to heat. And it's going to happen in the dark, right? No light. You're not shining ultraviolet light on it. You're not shining some kind of intense light source on here. So no heat, no UV. It's a different reaction, even though the starting materials look pretty similar. Okay, so now what happens here is once again that carbon-carbon double bond is going to be degraded to a single bond, and the elements of X will add across where the double bond used to be. See, the double bond is gone, but what's there now? A single bond. And what's new? We have the elements of X2 have added across where the double bond used to be. Bullet points for the reaction, right? So here, this is what I really want you to remember about this reaction. No carbocation intermediate. This is not a carbocation reaction. We will not see any rearrangements. Instead, we have a cyclic halogen. Hello. We have a cyclic halogen cation intermediate. What is that? We'll unpack all of that. Another characteristic of this reaction, more bullet points for the reaction, it's a trans addition. In other words, one of these x's, say if I'm dealing with a ring, one of these x's will be above, the other x will be below. It's a trans addition. All right, and then we have the cyclic halogen on the less hindered side. All right, so these are some of the bullet points for the reaction. So these all come out of the mechanism. So we'll look at the mechanism now. All right, so this is one of our favorite alkenes, and it's a favorite alkene for a couple of reasons. First of all, a lot of interest has been shown in this alkene because this is a dumbed down steroid. Maybe I showed you a slide of what the steroid structure looks like. So a steroid looks like this. You have these 4 rings like so. Right, so many steroids have that skeleton. So this is sort of like a dumbed down version of a steroid. A model compound, if you want to talk like a scientist. Another thing that this starting material, this alkene, another reason it's one of our favorites is because this double bond is sterically biased. The stick-up methyl group makes approach from the front more difficult than approach from the back. So we like this alkene because it allows us to test a lot of our stereochemical theories. Okay, so in halogenation, the first step is going to be the attack of the double bond on a molecule of X2 to form the cyclic halogen cation, right? Not a carbocation, but a cyclic halogen. So the double bond is the nucleophile. X2, this is the electrophile. But right away, this needs some explanation because in hydrohalogenation, we have HX, and we know that H is less electronegative than X. So for hydrohalogenation, it made sense that the nucleophile, the alkene, should attack the H part of HX. So who's more electronegative, Br or Br? It's equal electronegativity. Who's more electronegative, Cl or Cl? Equal electronegativity. Why does this function as an electrophile? Why? Where's the imbalance of charge? Well, so this first step needs some further explanation. So XX, this could be Br2 or Cl2 or something like that. The electron distribution in XX is symmetric. Neither atom is more electronegative than the other. But now, when the alkene gets into the picture, the alkene and its pi orbitals, right? That's the pi orbital of the alkene. As the alkene approaches X2, what is going to happen is that negative hates negative. This circle represents electrons, they're negative. These circles represent electrons, they're negative. As the alkene gets close to a molecule of X2, what is going to happen to X2 is that its electron distribution will rephase itself. So here's the alkene getting close. Here's the alkene getting close to X2. There are its pi orbitals. And now the electrons here around X2 are fleeing the incoming alkene. Negative hates negative. These circles represent electrons. As these electrons approach X2, the electrons of X2 are going to try to get as far away from the approaching alkene as possible. So we have more electrons over here than we have over here. In other words, this is partial negative and this is partial positive. We've set up the very same situation that we saw with HCl and HBr and HI. We have a positive end, we have a negative end of this molecule here. This is called an instantaneous dipole. And so this is why the double bond can attack a molecule that is composed of two atoms of equal electronegativity, because as the alkene gets close, the electrons are going to flee, getting out of its way. Okay. And so we get a cyclic halogen cation on the less hindered side of this carbon-carbon double bond. Okay, so like for example, I don't have any models here. I don't want to take time to make a model, but there's our alkene. There's our alkene. Maybe draw two hexagons on it. Right, here's our methyl group. It's on a wedge sticking up at you. Br2, is it going to approach from this direction? Is it going to approach from this direction? Nope, because that methyl group is in the way. It's easier for the halogen to come in from the back. So this is what I mean by cyclic halogen on the less hindered side. The back of this molecule is an easier approach than the front. We don't get a carbocation. What we get is this cyclic halogen cation on the less hindered side of the original alkene. It's cyclic because it's a three-membered ring. It's halonium because the positive charge is on the halogen atom. And the reason that this cyclic halonium forms and not a carbocation is because the halogens are big. They're much bigger than a proton is. So these halogens can sit on both of these carbons at the same time, no problem. Another virtue that this cyclic halonium has over the carbocation is everything has an octet here, right? In the carbocation has a carbocationic carbon that only has a sextet of electrons. Everything here has an octet. This is much more stable. But hydrogen can't do this. Hydrogen can't span two carbons at the same time. It's too small. But look where Cl, Br, and I are on the periodic table. These are big atoms. They can span both carbons at the same time. All right, so there's our cyclic halonium cation. Now we've had X minus swimming around in solution. And so now this three-membered ring here, it's strained. It wants to be busted open to relieve the strain. And so what this X minus is going to do is it's going to attack one of these carbons of the halonium ion. But which one? It's going to attack the more substituted carbon. So this guy now, X minus attacks the more substituted carbon of the cyclic halonium, because that's the carbon that most resembles a carbocation. That would be, if this were a carbocation mechanism, that's the carbon that would be attacked. It has more, it's more stabilized. Okay, but the direction of the attack is going to have to be anti or trans to where the X minus is. X minus attacks anti or trans to the X plus. That's just a steric. That's just a deduction that we can get from sterics, is that X minus wants to attack either this carbon or this carbon. It's going to attack this carbon because that's the more substituted carbon. But because you have this huge X plus atom in the back of the molecule, the X minus that is coming in, has to attack from the front. Yes, this methyl group is in the way, but the X plus is closer to the scene of the action. So the attack of the X minus will be there. And so the final product here is going to be, there's our original X. I'm going to put in square just to keep track of him. That's what used to be X plus. When X minus came in, it ruptured this bond, right? That's a three-membered ring. It wants to be busted open to relieve the strain. And the new X came in over here. And so notice that the stereochemistry is trans or anti. All right, so it's a very nice mechanism because it requires some visualization, and we also have these characteristics of the reaction that we need to keep in mind. Let's do some product prediction. Cl2, 25 degrees, dark. Draw the structure of the product. Clearly show all the dashing and wedging. So what are we thinking about in this reaction? Okay, we're thinking about how the product is going to have, the double bond gets knocked out. We're going to get CLs at both ends of where the double bond used to be. They're going to be trans addition. Okay, we can go through the mechanism, sure, why not? Double bond attacks Cl2. We get a cyclic halogen, cyclic halogen ion. So down here, we're going to have a little triangle tipped with Cl. Tell me in the chat, is that triangle, is that Cl triangle tipped with a positive charge? Is it going to be on dashes or wedges? Tell me in the chat. Where this double bond used to be, where this double bond used to be, we're going to get a cyclic chloronium ion. That's a little triangle with tipped with Cl plus. Is it going to be on dashes or wedges? 50-50 chance of being righteous by guessing. I see several people that fortune has not been with you. Dashes or wedges for that? Swear to God. Sorry about that, guys. Where's my Zoom? Here I am. I want to live in a cave. The Cl is going to be on dashes. The Cl plus is going to be on dashes because when we look at this molecule here, the back is defended by these two teeny tiny hydrogens. The front has this god-awful huge dimethyl cyclopropyl moiety on wedges. So I hope that you can see how the back is more sterically accessible than the front. Okay, so the Cl here lives on dashes. All right, so now it's time for the capture of the halonium ion, of the cyclic halonium ion by Cl minus. The Cl minus is going to attack one of the halonium carbons, and it's going to attack the more substituted one. And if the Cl plus is in the back, the new Cl has to come in from the front. So this guy is going to attack here, flinging the Cl open. And so our final product will be Cl. He's on a dash. He stays on a dash. New Cl came in from the front, so he has to live on a wedge now. And the pre-existing methyl group, well, we can't both be tops, right? So one of us has to be the top and one of them has to be the bottom. He was on the top, but the new Cl came in from the top. So that methyl group got shifted to the back. So this would be the product stereochemistry. So how'd that go? All right, let's try another. All right. Let's get in a chair, right? Good old chairs. BR2, 25 degrees dark. Draw the structure of the product, but I want to see a nice chair conformation. So first step in the mechanism is the formation of that cyclic bromonium cation. Tell me about that cyclic bromonium carbocation. Is it going to be a pointy up stalagmite, or is it going to be a pointy down stalactite? So what about that cyclic bromonium ion? Is it going to be pointing up or is it going to be pointing down? Tell me in the chat, stalagmite or stalactite? Yeah, it's going to be pointing down because the approach of the BR2 from the top is inhibited by this feature here, right? So here's BR. It's trying to get into that alkene. Whoa, look at that. Do you see how it got rejected by the stick-up feature here? Let's see that again in slow motion. It's just much easier to come in from the bottom. Okay, so this is going to be challenging to draw, I'm sure, for me and everybody. Whoa. Maybe something like that. The important point is that the cyclic bromonium came in on the less hindered side. Okay, so that was this. Now it's time for the Br minus to get involved, and it's going to attack the more substituted carbon. It's going to attack the more substituted carbon of the halonium, but it has to attack from the direction opposite the Br plus for steric reasons. Yes, this Br minus has trouble getting in here because of the stick-up feature, but it would have more trouble getting to this carbon by trying to somehow circumvent this Br plus. So it's going, the Br minus comes in on the, from the direction opposite this Br plus. Br minus comes in opposite. Okay, we're ready to draw the structure of the product. Wow, this mist. It's mist. It's supposed to look back. This Br is down it stays down. That means axial. This BR came in from the top. We're drawing a chair. We have axial and equatorial options. So the second BR is also axial, and that pre-existing methyl group got shoved down to the bottom into the equatorial position. And we see here trans addition of these two BRs. All right. So let me finish talking about halogenation and then move on to our next reaction. BR2, 25 degrees dark. Okay, so see, this is an alkene that doesn't have a more hindered side or a less hindered side. It has the approach from the front is equal to approach from the back. So you're going to get approach from in both directions with equal probability. All right, so let's write out the possibilities. So BR so there, that cyclic halonium came in from the front. But we have another possibility. We have another possibility where the cyclic halonium came in from the back. And this is going to happen with equal probability because this alkene doesn't have a more hindered side or a less hindered side. Our previous examples, because I was trying to explain the stereochemistry of the reaction, we had alkenes that had more hindered side and less hindered side, but this one doesn't have such. So we get attack from the front and attack from the back with equal probability. Now the BR that's swimming around in the reaction mixture is going to attack the more substituted carbon, but in the direction opposite the pre-existing halonium, and it breaks this halonium open. And so here, halonium was on wedges, so the new BR comes in on a dash. Okay, now it's not wrong to put a wedge here. That's not wrong to put a wedge there. It's just meaningless because this is not a chirality center, right? So it's not wrong to put wedges there. It just doesn't mean anything. Down here, what happened is the BR was on dashes. The second BR came in on a wedge. And once again, it wouldn't be wrong to put dash, dash, dash here. It just wouldn't mean anything because this is not a chirality center. Ordinarily, you know, that's where we really convey a lot of information with dashing and wedging when we have a chirality center. So what we see here is in this case where you don't have where the alkene is not hindered from the front or from the back, what we got here was a racemic mixture of two enantiomers. Okay, so I think there was what I'm hoping will be an instructive question in the chat. So the negative charge BR comes in on the more substituted C. Indeed it does. So we get a mixture of enantiomers here, and this could or could not be a disaster in the laboratory. We talked about how enantiomers in a physiological system where they're interacting with chiral enzymes, we talked about how enantiomers can either reduce pain and heal diseases or cause all kinds of havoc, right? So the fact that you get enantiomers here, this may or may not be a disaster. Okay, next reaction. Halogenation formation. All right, so the overall reaction here is going to be, we have our carbon-carbon double bond, and we react it with X2, right? And this is going to be either Br2 or Cl2 or I2. But in addition to that, we will have water present as well, right? In the earlier reaction, we didn't have any water. Now we're going to have water. And what happens here is, once again, that carbon-carbon double bond is degraded to a single bond. And you're going to get X at one end of where the double bond used to be, and OH at the other end of where the double bond used to be. This is called a halohydrate. It's a special kind of alcohol, right? It would be, it's an alcohol that happens to have a Cl or a Br or an I on the carbon next to the alcoholic carbon. All right, bullet points for the reaction. Cyclic halogen intermediate, just like we saw before. No carbocation. Trans addition of X and OH, right? Just like we see with halogenation, is the new X and the new OH. One of them is going to be a dash, one of them is going to be on a wedge. X on the less hindered side of the original carbon-carbon double bond. And of course, this means that OH on more hindered side of the original carbon-carbon double bond. And furthermore, OH on the more substituted carbon. All right, so these are the characteristics of this reaction that are explained by the mechanism, which we're going to go through right now. Cyclic halogen intermediate, trans addition, X on less hindered side. That's because that cyclic halogen forms on the less hindered side. OH attacks the more substituted carbon, and OH on the less hindered side. I mean, on the more hindered side. I'm going to put a big bad chicken foot up there at 12 o'clock. First step, ho-hum. It's just the formation of that cyclic halogen ion on the less hindered side of the original alkene. So I have this big bad chicken foot on a wedge. So that means that cyclic halogen will form on dashes, just the less hindered side. Dash, 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 X, dash, 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 X. Since the X plus is on dashes in the back of the molecule, that pre-existing methyl group got shoved to the front. It's now on a wedge. Okay, now what's supposed to happen what would happen in halogenation is now the X minus would attack the more substituted carbon and from the front. But we have water in here now. And I don't know, did anyone ever tell you what the concentration of water is in water? It's about 55 molar. Water's a nucleophile. I'm going to wrap this up in a minute. Water attacks you have a lot of water. The concentration of water in water is 55 molar. That's going to be much higher concentration than of bromine. So water attacks the more substituted carbon, and also since the X minus is in the back, the water has to attack from the front, shoving that pre-existing methyl group from a wedge now to a dash. And then last step is that X minus comes in, functioning as a base, and it's just going to deprotonate that oxonium ion. Oxygen doesn't like to have a positive charge on it. And so there's our product. There's our halogenation ion. The other product, the inorganic product of this reaction would be HX. Okay.